The question that I have is, what are the key weight-volume relations for soils? These are the objectives for this video. First, I will define soil from a soil mechanics point of view. Then I will define various weight and volume quantities we use in soil mechanics. Following that, I will derive some key weight to volume relationships. So let's start with the introduction. If I zoom in on a small volume of soil, what am I going to see? I'm going to see some solid particles, right? Like this. These are solid particles. And then in between the solid particles, we have what we call void. And this void generally could be filled with air and liquid. Most of the time, we deal with water as the liquid. But sometimes, of course, the liquid could be oil or benzene or glycerine or something like that. Like, for example, if I take a small sample right under the landfill, you are going to find all kinds of liquid in there. It could be benzene, glycerine, what have you. The following three scenarios are possible. First, there's no liquid in the void. We'll call such a soil as dry soil. Second, the void is completely filled with a liquid, and we'll call such a soil a saturated soil. And finally, the void could be filled with both air and liquid, and we'll call such a soil as partially saturated or unsaturated soil. These are called phases: solid, air, and liquid, and therefore there are three phases in soil in general. But the weight of air is negligible, and therefore for all practical purposes, soil is a two-phase medium. Why is it necessary for us to study the weight-volume relationships? One of the most important quantities in soil mechanics is the density of soil. So let me go ahead and first define it. The density is defined as mass over volume, whereas unit weight is defined as weight over volume. We'll use these notations here. Capital M for mass, capital V for volume, rho for density, and gamma for unit weight. We know from our basic physics, weight equals mass times G, mg, and therefore gamma is related to the density through these relationships. Gamma equals rho g, where g is the gravitational acceleration. Anybody remembers the unit weight of water? Well, if it's fresh water, it's 62.4 pounds per cubic foot, but if it's seawater, it could be a little higher, like 64.4, something like that. So if I take a box, cubic box of dimensions 1 by 1 by 1, and fill that completely with water, the weight of the box is going to be 62.4 pounds, right, by definition of density. And if I take the same box and fill it with a soil, what would be its weight? Well, it'll be easy for us to answer this question after we establish the weight-volume relations. Let's get a few other basics out of the way before we get into the weight-volume relations. Specific gravity. So this is the quantity that tells you how heavy a material is in relation to water. We are mostly interested in solid particles, so let me go ahead and define it for the solids that we have in soil. The specific gravity of solid particles is defined as the ratio between the unit weight of solid particle and the unit weight of water. This is the notation that I will use for specific gravity of solid, G sub S, S for solid particle. The average value of specific gravity for solid particles is about 2.7. It could be a little less, it could be a little more, but if you don't have a good value, you can always assume this to be about 2.7. Next, let me talk a little bit about dimensions and units that are relevant to what we want to do here. The primary dimensions that are relevant to soil mechanics are mass, length, and time. There are two systems of units, SI units and British units. The British units, also sometimes called English units or US customary units, but I'll refer to that as British units here. And these are the standard units in these systems. For example, in the SI units, we measure the mass in kilogram, length in meter, time, of course, in second. In British units, we measure the mass in slug, length in foot, and of course the time again is second. And these are the conversion factors between the two systems of units. So what about force? The Newton's law, F equals ma, serves as the basis for the answer to this question. In SI units, if you have 1 kilogram accelerating at 1 meter per second squared, the corresponding force will be 1 Newton. And in British units, if 1 slug is accelerating at 1 foot per second squared, the corresponding force will be 1 pound. The conversion between pound and Newton is this. Now we are ready to delve into the weight-volume relations. As we have seen before, soil consists of solid, air, and water. The first thing we want to do is to represent these phases in a diagram called phase diagram. The phase diagram is partitioned into solid, water, and air. We will derive these relations by considering just water as the liquid, but the relationship can be easily extended for other fluid like oil or benzene. I want to mark the fractional volumes on the left side and the fractional weights on the right side. V sub A is the volume of air, V sub W is the volume of water, V sub S is the volume of solid, and the total volume is V. And on the right side we have 0 for the weight of air. Obviously we are neglecting the weight of air. Weight of water is WW. Solid, weight of solid is W sub S. Total weight is W. It turns out that the derivation of weight-volume relations become a lot easier if I assume that the volume of solid is 1. I'll come back and fill these quantities after I define some basic quantities. So these are the 3 volume quantities of interest for us. Void ratio, defined as the ratio between volume of void and the volume of solid. Now going back to this diagram, since we have taken the volume of solid as 1, the volume of void must be E. Now the definition of porosity. Porosity is defined as the volume of void divided by the total volume. Again, going back to this diagram one more time, the volume of void is E. The total volume is 1 plus E. So now we have a relationship between porosity and void ratio. Now the degree of saturation. Degree of saturation is defined as the volume of water divided by the volume of void. Now going back to this diagram again, we know the volume of void is E, and therefore the volume of water must be equal to S times E. Now we can fill up the right side of the phase diagram. Weight of air is 0. Weight of water is volume multiplied by the density of water. So that must be S times E times gamma W. Weight of solid is volume multiplied by the density of solid again. So volume is 1 and the density of solid in terms of specific gravity is G sub S times gamma W. Now let's look at some weight quantities. The water content is defined as the ratio between the weight of water and weight of solids. And this is the notation that I will use. Now going back to this diagram one more time, you can see that the water content can also be written as weight of water, which is SE times gamma W, SE times gamma W, divided by weight of solids, which is GS times gamma W. And the gamma W's cancel out, and we have a simple relationship for the water content, which is omega equals SE over G sub S. Now we are ready to talk about various measures of unit weight. Let's start with the total unit weight. In defining the total weight, we don't look at the details of what we have inside the soil. We just take the total weight and divide that by the total volume. The total weight is SC times gamma W plus G sub S times gamma W. Since I have gamma W in both terms, I can factor that out. The total volume is 1 plus E. So now we have an equation for the total density. Total density is a function of the specific gravity of solids, degree of saturation, weight ratio, and the density of water. So this quantity right here can be thought of as a specific gravity for the total density. It basically tells you how heavy the soil is in comparison to water. Another measure of density that we are interested in soil mechanics is the density of a dry soil, gamma sub D. In this case, the weight of the soil will simply be G sub S times gamma W, and the total volume is still 1 plus E. So this is the equation for the dry density. We can relate the total density to dry density through water content as follows. You guys follow what I did over here? I took the equation for total density, and for SE, from this equation right here, I substituted omega times GS. So I have GS in both terms here. That could be pulled out, and then the equation simplifies to this, and this of course is the dry density, right? And therefore total density therefore becomes equal to 1 plus omega times the dry density. And this is a very useful relations. We'll be making use of this a lot in the section on compaction. Next, saturated unit weight. When the soil is fully saturated, there's no air in there. The volume of void then becomes equal to the volume of water, and therefore degree of saturation becomes equal to 1. I can substitute 1 for the degree of saturation in this equation right here, and write down an equation for the saturated unit weight. The final density measure that we are interested in soil mechanics is what is called the submerged or buoyant density. So this density is relevant if the soil is completely submerged. Its use will become clear when we start talking about stresses in soil. So this is one of the notation that is commonly used. This is another notation that is commonly used. Basically, buoyant density equals the saturated density minus the density of water. So if you go through and simplify this a little bit, you get this equation for the buoyant density. Let me also point out that the weight ratio can be greater than 1, whereas porosity cannot be. So let's look at the definition of porosity one more time. The porosity is defined as the volume of void divided by the total volume, right? So let's consider a case where the void expands and fills the whole volume. Then the ratio between the two becomes equal to 1, which is the maximum value for porosity. And therefore, N has to be less than or equal to 1. Let's consider the other extreme, where there is no void in the soil. So in that case, volume of void is 0, and therefore the porosity works out to be 0, which is the other limit of the porosity. Porosity basically lies between 1 and 0, but there is no such restriction for void ratio. So the void ratio can be greater than 1. And it usually happens for very loose clay, like the clay in Mexico City, for example, has a very large void in it, and the void ratio of that soil is extremely high. I'd like to talk about one more quantity that is commonly used for cohesionless soils like sand. This is the quantity called relative density. So this is how it's defined. Relative density equals E max minus E over E max minus E min times 100%. So usually we express that as a percentage. Here E max is the void ratio corresponding to the loosest possible packing. And E min is the void ratio corresponding to the densest possible packing, and E is the actual current void ratio of the sample at hand. So it's clear when the void ratio is equal to the maximum void ratio, then from this equation we see the relative density is going to be 0, whereas when E equals E min, this and this term becomes equal to each other, relative density works out to be 100%. And therefore, relative density is seen to lie between 100% and 0%. 0 for very loose to 100 for very dense. And this idea is extensively used in liquefaction analysis, because we know the very loose saturated sand tend to liquefy, whereas dense sands will not. And therefore, relative density of the material kind of tells you whether a saturated sand that you have in the site is going to liquefy or not during maybe an earthquake.